Welcome back to Secure 7, your hub for learning cybersecurity, penetration testing, and ethical hacking from scratch. In today's video, we'll be exploring server-side request forgery, also called SSRF. This is one of the most dangerous and underestimated vulnerabilities in modern applications. Why? Because it allows an attacker to make a server perform HTTP requests that the attacker controls. This opens the door to internal network scanning, access to cloud metadata services, credential theft, and even full system compromise. We'll break it all down step by step: what SSRF is and why it's dangerous, real-world case studies where SSRF caused multi-million-dollar breaches, a DVWA-style lab demonstration, the attacker's perspective, how hackers use SSRF to escalate attacks, defenses and mitigation strategies to protect your systems. Stick with me till the end because you'll not only understand SSRF, but you'll also be able to spot and prevent it in real applications. Let's start with the basics. Server-side request forgery occurs when a web application takes a user-supplied URL or resource location, and the server itself makes an HTTP request based on that input without proper validation. This means the attacker can control where the server connects. For example, a website has a feature where users can fetch a preview of a link. The application takes a URL parameter from the user, then uses functions like getContents or curl in PHP to fetch the web page. If there is no restriction, the attacker can provide malicious input. Instead of a normal external link, they provide http:/localhost/admin. The result? The server fetches its own internal admin panel and shows the content to the attacker. This bypasses network protections because the request comes from the server itself inside the firewall. Analogy: think of SSRF like tricking a librarian. Normally, you can ask them to bring you a book from the public library, but if they don't check properly, you could tell them, go to the private archives in the basement and bring me the confidential files. And because they trust your request, they do it. That's SSRF in a nutshell. Now let's see how SSRF has been exploited in the real world. Case 1, Capital One Breach 2019. A misconfigured AWS Web Application Firewall (WAF) allowed an attacker to exploit SSRF. The attacker sent crafted requests that made the WAF query AWS instance metadata. They retrieved temporary IAM role credentials. Using those credentials, the attacker accessed S3 buckets and downloaded over 100 million credit applications. This breach cost Capital One over $150 million in damages. Case 2, Uber Bug Bounty 2016. A researcher discovered that Uber had an endpoint which fetched images from external URLs. By supplying crafted requests, the researcher was able to make Uber's server access internal infrastructure. This SSRF bug earned the researcher a $10,000 reward on the Bug Bounty program. Case 3, Shopify Bug Bounty. In Shopify, SSRF vulnerabilities were found in their PDF and image rendering features. Attackers could use them to probe internal endpoints like HTTP 7.0.1 where internal services were running. Shopify paid high bounties. Some SSRF reports went up to $15,000 plus. Case 4, Jira GitHub Slack SSRF findings. In some cases, SSRF was used to access cloud metadata endpoints like http://16.254.254/latest metadata in AWS. From there, attackers exfiltrated API keys, tokens, and secrets. Let's see SSRF in action with a vulnerable demo application. From an attacker's perspective, SSRF is one of the most powerful bugs because it acts as a gateway to hidden systems. Here's how attackers chain SSRF. 1. Recon. They find an endpoint that accepts a URL parameter. 2. Internal scanning. They test localhost and private IP ranges like 127.0.1, 10.x.x, 2.168.xx. 3. Cloud exploitation. They target metadata endpoints in Azure, GCP. 4. Credential harvesting. They grab API keys or IAM credentials. 5. Privilege escalation. With those keys, they interact with storage, databases, or even start new instances. 6. Persistence. They upload malicious files or create new accounts with admin privileges. SSRF often doesn't stop at just fetching a URL. It's a pivot point that attackers use to escalate into full-blown infrastructure compromise. So how do we protect against SSRF? Here are some strong defense mechanisms. 1. Input validation and whitelisting. Only allow requests to trusted, predefined domains. Example, if you only need to fetch product images from cdn.myshop.com, restrict input to that domain only. 2. Block private IP ranges. Deny requests to internal IP addresses like 127.0.0.1, 10.x.x.x, 192.168.xx, and cloud metadata IPs. 3. Use a URL fetch proxy. Instead of letting the app directly fetch URLs, pass requests through a secure proxy that enforces rules. 4. Disable dangerous functions. Avoid using raw functions like fileGetContents or curl exec directly with user input. 5. Cloud security hardening. Enable IAM-DSv2 in AWS, which requires session-based tokens to access metadata. In GCP and Azure, restrict metadata APIs with authentication. 6. Network segmentation. Place strict firewall rules so web servers cannot directly talk to internal services or databases. 7. Monitoring and detection. Log outbound requests. Alert when unusual requests are made to localhost or metadata services. To summarize, SSRF happens when a server makes requests based on unvalidated user input. Attackers can use it to access internal networks, cloud metadata, and credentials. Real-world breaches like the Capital One hack show the devastating impact. Bug bounty hunters have made tens of thousands of dollars finding SSRF bugs. Defenses include strict input validation, whitelisting, blocking private IPs, cloud hardening, and logging. This is why SSRF is ranked in the OWASP top 10. The impact can be critical. If you enjoyed this breakdown, hit the like button, subscribe to Secure 7, and don't forget to check out my Ethical Hacking Basic course on this channel to strengthen your cybersecurity foundation. Thanks for watching, and I'll see you in the next vulnerability deep dive. Welcome to Secure 7. In today's episode, we'll break down one of the most dangerous web vulnerabilities from the OWASP top 10, broken access control. We'll show you how it works, why it's so dangerous, demo real-world scenarios, and teach you how to prevent it. Before we break it, let's understand what access control is. Access control defines who can do what in a system: view profiles, edit posts, access admin panels, or delete users. Types of access control: role-based, RBAC, access based on user roles; attribute-based, ABAC, based on user properties; discretionary, DAC, set by the resource owner; mandatory MAC, based on system-enforced rules. When these controls aren't implemented properly, users can access or perform actions they shouldn't. That's broken access control. Let's say you're logged in as user A and your profile URL is /example.com/user123. But what if you change 123 to 124 and see another user's data? That's an IDOR, Insecure Direct Object Reference. With IDOR, attackers can view or modify data they shouldn't have access to: user emails, orders, invoices, even passwords. To find broken access control issues, ethical hackers use tools like Tools List. Burp Suite, repeater, intruder, proxy, OWASP Zape, Postman for manual API testing, FFW for endpoint fuzzing, Autorize Burp plugin to test access with different tokens. These tools help test how the app behaves when different users try to access protected resources. There are several forms of broken access control. 1. Vertical privilege escalation. Regular user becomes admin changes in cookies or roles. 2. Horizontal privilege escalation. User accesses another user's data, changing user ID in URLs or requests. 3. Forced browsing. Accessing restricted resources just by knowing the URL. 4. Missing function level. Access control API endpoint lets anyone delete a user or create an order without checks. 5. Bypassing access controls with method tampering using post instead of get or JSON instead of form data to bypass logic. Now the big question, how do we prevent this? Implement role checks on every request. Every API call or route must verify user permissions. Use secure ID handling. Avoid exposing sequential user IDs. Use UUIDs. Deny by default. Block access unless explicitly allowed. Enforce access control on server side only. Never rely on client-side checks like JavaScript or hidden fields. Audit and test regularly. Use automated scanners, manual pen tests to catch gaps. Log and monitor access control violations. Spot strange behavior in logs before it becomes a breach. Broken access control is responsible for many real-world breaches. Real cases: Facebook, IDOR exposed user photos in private albums. Instagram, user data accessible by changing mobile API requests. GitHub, developers accessed repositories of other organizations. These bugs often go unnoticed but can be catastrophic. Let's recap. Broken access control happens when users access data or features beyond their role. Includes IDOR, privilege escalation, forced browsing, can be detected using Burp, Zap, Postman, and plugins. Prevented with strict role checks, proper session handling, and audits. It's one of the most common findings in bug bounty programs. Thanks for watching Secure 7. If this helped you, smash that like button, subscribe for weekly hacking content, and share it with your fellow learners. Next up, we'll cover cross-site scripting, XSS, another dangerous web bug with powerful impact. Stay secure. Stay ethical. Welcome back to Secure 7. In today's session, we'll explore one of the most dangerous OWASP top 10 vulnerabilities, broken authentication, also called identification and authentication failures. Hackers love this flaw because it allows them to steal logins, hijack sessions, and completely take over user accounts. Stay tuned as we break it down with real examples and a live DVWA demo. Quote, broken authentication occurs when an application's login or session management system is poorly implemented. This can happen if passwords are weak or predictable, login forms don't protect against brute force, sessions are not properly secured. When this happens, attackers can impersonate legitimate users, escalate privileges, or even hijack admin accounts. You might think this only happens in theory, but real-world breaches prove otherwise. For example, in 2021, attackers reused stolen credentials from other sites to compromise thousands of accounts in credential stuffing attacks. In another case, session cookies were stolen over insecure HTTP, allowing attackers to impersonate users. These incidents cost companies millions and destroyed trust. Let's see how brute force works using DVWA, Damn Vulnerable Web App. DVWA has a deliberately insecure login form. Using tools like Burp Suite or Hydra, hackers can send thousands of username, password combinations automatically. If there's no account lockout or rate limiting, eventually they'll find the right password. Credential stuffing is even easier. Attackers use leaked username password pairs from past breaches. Many users reuse the same password across multiple sites, so one leak leads to many hacked accounts. Broken authentication isn't just about passwords. Even after login, your session needs protection. Imagine you log into an HTTP site. Your session cookie travels in clear text. A hacker using a network sniffer like Wireshark can grab that cookie. Once they have it, they don't need your password. They just paste the stolen cookie into their browser and they're logged in as you. This is called session hijacking or session fixation. Other common issues include password reset links that don't expire or are predictable, multi-factor authentication bypass due to weak implementation, hard-coded credentials inside code repositories. All of these make authentication easy to break. Quote, so how can developers prevent broken authentication? 1. Use strong password policies. Enforce minimum length and complexity. 2. Add account lockouts or rate limiting to stop brute force. 3. Always enforce HTTPS to encrypt credentials and session IDs. 4. Implement multi-factor authentication, MFA. 5. Use secure random session IDs and invalidate them after logout. 6. Secure password reset flows with random tokens that expire. Following OWASP recommendations greatly reduces your attack surface. Broken authentication is one of the most exploited vulnerabilities today. Weak passwords, unprotected sessions, and poor configurations put your users and business at risk. The good news? By applying proper security controls, you can protect against these attacks. If you found this video helpful, hit like, subscribe, and share it with your team. Stay tuned on Secure 7 for our next episode in the OWASP Top 10 series. Welcome back to Secure 7. In today's episode, we are going to explore one of the oldest and most common attacks in cybersecurity, the brute force attack. It may sound simple, but it's still widely used by attackers today, and shockingly, it still works against many systems. By the end of this video, understand what brute force is, how it works, see a demo, and learn the best defenses. What is a brute force attack? A brute force attack is when an attacker tries multiple combinations of usernames and passwords until they find the correct one. Think of it as trying to unlock a door by attempting every possible key until one finally opens it. There are different styles of brute force attacks. A simple brute force is just trying every possible combination. A dictionary attack is when attackers use a pre-built list of common passwords, like 123456 or password 123. Credential stuffing is when attackers use leaked usernames and passwords from other websites, hoping people reuse them. How brute force works: imagine a login form that doesn't have any protections. An attacker can use automated tools like Hydra, Burp Suite, or custom scripts to send thousands of login attempts in a very short time. If the site allows unlimited attempts, eventually the attacker is likely to get in. Some attackers go further and use botnets, thousands of hacked computers working together to try different combinations. This makes brute force attacks even faster and harder to stop. Real-world examples. Let's look at some real-world cases where brute force was used. Twitter has been a frequent target of brute force attempts, especially on high-profile accounts. In the past, attackers tried password spraying, using a few common passwords across many accounts to avoid detection. LinkedIn has suffered from massive credential stuffing attacks. After data breaches, attackers reused millions of leaked passwords to break into other accounts, since people tend to use the same password everywhere. WordPress sites are also common victims. Hackers use automated bots to try default admin usernames like admin or root, along with weak passwords. If successful, they gain full control of the website. These cases show that brute force is not just theory, it happens daily, even against big companies. Demo in DVWA. Now let's see how a brute force attack works using DVWA, the damn vulnerable web application. Step 1. We log into DVWA and set the security level to low. Step 2. Go to the brute force section. We see a simple login form asking for username and password. If we try a random guess like admin and password, it fails. But since the application doesn't block us, we can keep trying. The login is successful and we now have access. This demonstrates how easy brute force can be when protections are missing. At higher DVWA security levels, protections like delays or lockouts are added, making brute force harder. This shows how important defenses are. Why brute force still works. You may wonder why such a simple attack still works in 2025. The answer is weak passwords and lack of protections. Many users still use passwords like QWERTY or Welcome13. Many systems still don't have two-factor authentication, and some developers don't add basic defenses. Attackers know this and take advantage of it. How to defend against brute force. Now let's talk about defenses. First, enforce strong password policies. Require longer, complex passwords and encourage passphrases that are easy to remember but hard to guess. Second, add account lockouts or rate limiting. After a few failed attempts, temporarily block the account or slow down responses. Third, implement CAPTCHA challenges to stop automated bots. Fourth, always enable multi-factor authentication. Even if a password is guessed, the attacker still needs the second factor. Fifth, monitor login attempts. If you see hundreds of failed logins from the same IP, block it. Finally, educate users about password reuse. If one site is hacked, attackers shouldn't be able to reuse the same password everywhere. Recap and conclusion. Brute force attacks are simple but powerful. We learned what they are, how they work, saw examples, ran a DVWA demo, and discussed defenses. The key takeaway is this: never underestimate simple attacks. Protect your accounts with strong passwords, multi-factor authentication, and security controls. That's it for today's episode on brute force attacks. If you found this useful, hit like, share it with your friends, and subscribe to Secure 7 for more cybersecurity lessons. And don't forget to check out our Ethical Hacking Basics course on the channel. Thanks for watching and stay secure. Hey everyone, welcome back to Secure 7. In this video, we're diving deep into one of the most dangerous web vulnerabilities from the OWASP Top 10, command injection. It allows attackers to execute system-level commands directly on your server, potentially giving them full control. We'll break it down, show a real demo using DVWA, and discuss how you can protect your applications. Let's start simple. Command injection occurs when user input is passed directly to a system shell command without proper sanitization. That input can include special characters like a semicolon, double ampersand, or pipe to chain additional commands. For example, suppose a web app lets you ping an IP address entered by a user. If it just appends the user's input to a system command, an attacker can sneak in extra commands. Let's say the user inputs 127.0.0.1, that's fine. But if the input is 127.0.1 semicolon ls, the app will run both ping and list all files in the current directory. This is how a simple oversight can become a serious security flaw. Let's look at some real-world command injection attacks. In 2021, GitLab had a critical vulnerability where attackers could inject commands through CI configuration files, gaining remote execution. Cisco routers were also found vulnerable via their web interface, allowing remote users to run shell commands. Trend Micro's Apex Central product had a flaw that let attackers gain root access using malicious API calls. These are high-profile examples, proving command injection is not just theory, it's exploited in the wild. Let's move to a demo using DVWA, the Damn Vulnerable Web App. After logging in, we'll set the security level to low, then navigate to the command injection section. First, we enter 127.0.1. The page executes a ping command on that IP. Now, let's try injecting a command. We enter 127.0.1 semicolon ls. This time, the server pings the IP and also lists the directory contents, proof that our injected command was executed. If you're using Windows, you can try double ampersand followed by DR instead. This shows how dangerous it is when inputs go unchecked. Now let's explore how attackers take things further. By injecting a reverse shell command, the attacker can make the server call back to their system and open a remote session. For example, on Linux, a simple bash one-liner connects back to the attacker's IP and port. Once the connection is made, the attacker has a terminal with access to the server's file system and potentially even root privileges. This turns a small form input into a full server compromise. Terrifying, right? Now, how do we prevent this? First, avoid using system commands whenever possible. Use safer built-in functions or libraries to handle operations. Second, always validate and sanitize user input. Filter out dangerous characters like semicolons, pipes, and ampersands. Whitelisting is far more secure than blacklisting. Third, if you must use system commands, make sure to properly escape arguments using safe methods in your language, like escape shell arg in PHP. Next, follow the principle of least privilege. Your web server should never run as root. Limit what it can access, just in case something gets through. Finally, consider using a web application firewall. It can detect suspicious patterns and block dangerous payloads before they reach your backend. Misconceptions. One major misconception is relying on JavaScript validation. Client-side validation can be bypassed easily using tools like Burp Suite or curl. Attackers don't use the browser like normal users. They craft raw HTTP requests and insert whatever they want. The server should never trust client-side checks. Let's recap. Command injection is when an attacker can make your server execute OS-level commands. It's been used in real attacks on companies like GitLab and Cisco. We demonstrated how even a simple semicolon can open the door, and we showed how this can escalate into a reverse shell with full system access. But with proper validation, secure coding practices, and system hardening, you can prevent it. If you found this valuable, hit like, subscribe to Secure 7, and check out our full Ethical Hacking Basic course. Stay curious, stay secure, and keep hacking the right way. Welcome to Secure 7. Today we're diving into a sneaky but powerful web vulnerability, cross-site request forgery, or CSRF. We'll explain how it works, demonstrate real-world attacks, and most importantly, show you how to prevent them. Let's get started. CSRF is an attack where a malicious site tricks your browser into performing unwanted actions on a site you're already logged into without your knowledge. Imagine being logged into your bank. Then you visit a malicious site and boom, money is transferred without you ever clicking send. The attacker abuses your browser's session. They can forge requests on your behalf because your session cookies are automatically sent. It's like writing a check and someone else signing it with your pen without your consent. Let's demonstrate a CSRF attack using DVWA, Damn Vulnerable Web App. Here's how CSRF works in steps. 1. Victim logs into a target site, e.g. banking site. 2. Session cookie is stored in the browser. 3. Attacker crafts a malicious request, usually a form or AJAX call. 4. Victim visits attacker's page. 5. Browser sends the request with a session cookie. 6. Action gets completed, silently. No credentials, no password prompts, just abuse of trust. CSRF has hit real companies. Netflix, CSRF allowed attackers to change account settings. YouTube, old API, CSRF could subscribe users to channels. ForgeRock, an open redirect plus CSRF led to full account hijack. It's dangerous because it often goes unnoticed until it's too late. Several tools help pentesters find and exploit CSRF flaws. Burp Suite, intercept and replay CSRF payloads. OWASP Zap, passive scanning for vulnerable endpoints. CSRF Tester, simple test generator. Browser dev tools for crafting and sending hidden requests. The good news? CSRF is preventable with these defenses. Anti-CSRF tokens. Add unique tokens to each form/request. The server checks if the token matches. If not, the request is rejected. Same-site cookies. Set cookie headers like same-site equals strict or lax. This stops cross-origin requests. Set a value in both cookie and form. Compare both on the server. User interaction validation. Use CAPTCHAs or confirmation pages before sensitive actions. CORS headers refer checks. Restrict where requests can originate from. Log out. Idle sessions. Limit time attackers have to exploit the active session. CSRF can go beyond forms. It can target REST APIs, JSON requests, mobile apps with web views. Attackers might chain CSRF with XSS to steal CSRF tokens and escalate attacks. Let's recap. CSRF tricks your browser into doing things you didn't intend. The key problem is trust in cookies and sessions. With proper tokens, headers, and validation, CSRF becomes powerless. Don't ignore it. Even read-only actions can lead to privilege escalation. Thanks for watching Secure 7. If this video helped you, drop a like, share it, and subscribe for more hacking insights. Next episode, Insecure Deserialization, where we show how serialized objects can lead to remote code execution. See you next time. Welcome to Secure 7. In today's episode, we're diving into one of the most common and underestimated vulnerabilities on the web, cross-site scripting, or XSS. We'll break down how it works, the types of XSS, live demos, tools used for exploitation, and most importantly, how to defend against it. Let's get started. Cross-site scripting happens when attackers inject malicious scripts into websites that get executed in the browser of another user. That script could steal cookies, session tokens, or even perform actions on behalf of the victim. Let's say you visit a blog with a comment section, and a malicious user posts. You can see the code in our conversation history. If the website doesn't filter this input, the script runs when others view the comment. Now imagine if instead of an alert, the attacker injects JavaScript to steal your session cookie and sends it to a remote server. That's serious. There are three main types of cross-site scripting. Stored XSS. Malicious script is permanently stored on the server, like in forums, comment boxes, or product reviews. Every user who visits the page gets affected. Reflected XSS. The script is embedded in a URL and reflected off the server in an error message, search result, or any other response. Example, you can see the code in our conversation history. DOM-based XSS. This one doesn't even require server interaction. It exploits the browser's document object model, often through JavaScript functions like inner HTML. Let's demonstrate a basic XSS attack using DVWA, Damn Vulnerable Web Application. Navigate to the XSS stored section. Enter this in the input box. You can see the code in our conversation history. Submit and revisit the page. Boom, we see a pop-up. That's a stored XSS in action. Now replace that with something more stealthy. You can see the code in our conversation history. That script silently sends your cookies to the attacker's server. That's how sessions get hijacked. Ethical hackers use to test for and exploit XSS vulnerabilities. Common tools: Burp Suite, intercepts and modifies HTTP requests. OWASP Zap actively scans web apps for XSS. XSS Strike, automated tool for fuzzing and detecting XSS. XSS Hunter, great for blind XSS detection. Postman Curl for crafting custom payloads. So how do we stop XSS? Input sanitization, always filter user input. Strip or escape HTML tags and special characters like output encoding. Encode output based on where it's used: HTML, JavaScript, CSS, or URLs. Use secure libraries. Use libraries like DOM Purify to clean user-generated content. CSP, Content Security Policy. CSP headers can prevent scripts from running unless from trusted sources. HTTP-only cookies. Set session cookies as HTTP only so JavaScript can't access them. Framework features. Use modern frameworks like React or Angular. They escape output by default. Let's look at some real incidents. eBay. Persistent XSS in product listings allowed attackers to inject phishing pages. British Airways. XSS was used to steal payment info, leading to a major GDPR fine. Twitter. A self-retweeting worm spread via XSS in profile bios back in 2009. XSS isn't just a pop-up, it can cost millions. If you're into bug bounty, XSS is a goldmine. Tips: look for unsanitized input in search, comments, or profile forms. Try payloads like, you can see the code in our conversation history. You can see the code in our conversation history. Check for DOM XSS using browser dev tools. Use platforms like HackerOne or BugCrowd to report and earn rewards. Let's recap. Cross-site scripting lets attackers run scripts in other users' browsers. It can lead to cookie theft, phishing, malware, or full account takeover. CAD. Prevent it with input sanitization, output encoding, CSP, and secure frameworks. It's one of the most reported web bugs for a reason. Thanks for watching Secure 7. If you learned something today, give us a like and subscribe for weekly cybersecurity content. Comment below if you've ever tried finding XSS on a real website. Next up, we cover insecure deserialization, another sneaky vulnerability that can lead to remote code execution. See you in the next one. Welcome back to Secure 7, where we break down real-world hacking techniques and teach you how to defend against them. Today, we're focusing on a silent but deadly vulnerability in the OWASP Top 10, security logging and monitoring failures. Unlike flashy exploits like SQL injection, this weakness often lurks in the shadows, allowing attackers to remain inside a system for months or even years without being detected. By the end of this video, you'll understand what this failure is, why it happens, see real-world examples, watch a demo, and learn how to protect your organization. What does logging and monitoring mean? Before we discuss the failure, let's clarify what security logging and monitoring are. Logging means recording events that happen on a system. Logins, logouts, failed login attempts, file access, errors, configuration changes, basically anything that helps reconstruct what happened later. Monitoring means actively reviewing these logs, preferably in real time, using tools that analyze patterns and trigger alerts when something suspicious happens. Together, they form the backbone of detection. Without logs, you can't know an attack even happened. Without monitoring, you might have the logs, but no one notices the red flags until it's too late. Why failures are dangerous. Security experts say you can't protect what you can't see. If you're blind to malicious activity, attackers have free rein. They can move laterally, escalate privileges, exfiltrate data, and cover their tracks. Many companies focus all their budget on firewalls and antivirus, but forget the basic question: would we even notice if someone broke in? Real-world examples. In 2013, attackers breached retail giant Target via a third-party HVAC vendor. Once inside, they moved through the network for weeks. The shocking part, Target's security systems did generate alerts, but no one acted on them. 40 million credit and debit card numbers were stolen. Poor monitoring of security alerts and inadequate processes to respond cost Target over $200 million and lasting reputation damage. Equifax was breached through an unpatched Apache Struts vulnerability. Logs existed, but nobody correlated intrusion attempts with active exploitation. The breach went undetected for 76 days. Sensitive personal data of 143 million people, social security numbers, credit reports, was compromised. Capital One 2019 breach. A misconfigured firewall allowed access to an AWS S3 bucket. Because monitoring was insufficient, the breach wasn't discovered internally. It came to light only after the hacker bragged online. The lesson is clear. Even cloud environments need robust logging and monitoring. Notice a pattern? In all three cases, there were either missing logs, no correlation of data, or alerts ignored. Detection delay makes response meaningless. If logging is so important, why do organizations fail? Common reasons include 1. Logging the wrong events. Apps record trivial info messages but not failed logins or access to sensitive files. 2. No centralization. Logs are scattered across servers, making cross-system analysis impossible. 3. Lack of alerting. Even if logs exist, no automated monitoring or CM integration means anomalies go unnoticed. 4. Retention problems. Logs overwritten every few days leave no forensic trail. 5. Skill gaps. Teams lack staff trained to review and interpret logs effectively. Demo concept. Let's walk through a simple demo to illustrate logging failure. We'll use DVWA, the Damn Vulnerable web app. Imagine an attacker trying multiple wrong passwords to brute force a user's account. In a properly monitored system, these failed logins would be logged and trigger an alert after several attempts. In DVWA, by default, no such logging occurs. We run Hydra or Burp Intruder to brute force the login. There are 0 alerts, no security team notifications. This is how attackers stay under the radar. If the attacker succeeds and logs in as admin, still no alerts. That's a perfect example of monitoring failure. Now, what should happen? Logs should be sent to a centralized system like Elk or Splunk with an automated rule: 5 failed logins in 2 minutes, trigger SOC alert. This simple change drastically reduces attacker dwell time. How to fix it? Here are concrete steps to prevent logging and monitoring failures. 1. Log the right events: failed logins, privilege escalations, file access, errors. 2. Centralize logs. Use a SIEM, security event management system like Splunk, ELK, Graylog. 3. Automate alerts. Define thresholds and trigger alarms for anomalies. 4. Protect logs. Secure them from tampering. Attackers love to erase their tracks. 5. Retain logs. Keep logs for at least 90 days or as per compliance. 6. Test your monitoring. Simulate attacks to see if your system detects them. Red team exercises help. These aren't just best practices, they're essential to detect intrusions before they become massive breaches. Security logging and monitoring failures may not get the spotlight like SQL injection, but they're the reason attackers succeed silently. The average detection time for a breach is over 200 days, nearly 7 months of unnoticed activity. Don't let that be your organization. Implement robust logging, monitor actively, and test regularly. Remember, you can't protect what you can't see. If you found this video helpful, like it, share it, and subscribe to Secure 7. In our next video, we'll cover another OWASP Top 10 vulnerability with demos and real-world cases. Welcome back to Secure 7. In this video, we'll explore another OWASP Top 10 vulnerability: security misconfiguration. This is one of the most common and dangerous weaknesses in cybersecurity. By the end of this session, you'll understand how it works, see a live DVWA demo, and learn how to protect against it. What is security misconfiguration? Security misconfiguration happens when systems or applications are deployed with unsafe default settings, unnecessary services, or excessive permissions. Even if your application code is secure, a bad configuration can make you vulnerable. Some common examples include leaving default admin usernames and passwords unchanged, running the application in debug mode in production, exposing directory listings or sensitive files, improper CORS configuration allowing unauthorized cross-origin requests. Attackers love misconfigurations because they're often the easiest way in. There are many high-profile breaches caused by simple configuration mistakes. In the 2017 Equifax breach, a vulnerable Apache Struts setup led to the compromise of personal data for over 140 million people. Companies like Uber and Accenture have leaked sensitive data because their cloud storage buckets were left public. Even Kubernetes dashboards have been exposed online without authentication, allowing attackers full control. Now let's look at how security misconfiguration works using DVWA, the Damn Vulnerable Web Application. Step 1. Log in to DVWA with admin credentials and set the security level to low. Step 2. Go to the File Upload module. Normally it asks for an image file, but because of weak validation, we can upload a PHP shell instead of an image. After uploading, we access the uploaded file directly from the server and execute system commands remotely. This gives us remote code execution, all caused by misconfigured file upload settings. Another example, directory listing is enabled on this server. By visiting the Uploads folder, we can see all uploaded files without authentication. At higher DVWA security levels, these misconfigurations are fixed, file types are validated, and directory listing is disabled. This shows how important proper configuration really is. Other misconfiguration examples. Beyond DVWA, there are many other examples. Devices and IoT systems left with default credentials like admin, verbose error messages exposing stack traces and database queries, leaving unnecessary services like SSH or MySQL open to the internet with weak security. Impact of misconfiguration. The impact can be devastating. Attackers can steal sensitive files like environment variables and configuration files. They can gain remote shell access and escalate privileges. Sometimes a simple misconfiguration allows a complete server takeover. It's like leaving your house unlocked with the keys under the doormat. Even if you have strong walls and cameras, it doesn't matter if the door is wide open. How to prevent security misconfiguration. The good news is, most misconfigurations are easy to fix if addressed early. Here are some key steps. Change all default passwords and secret keys before deploying. Disable directory listing and restrict upload paths to safe locations. Follow the principle of least privilege. Give only the permissions and services necessary. Turn off debug mode in production. Use security headers like Content Security Policy and X-Frame options. Regularly run automated security checks with tools like Linus, Scout Suite, or OWASP Zap. Security misconfiguration is one of the simplest but most dangerous vulnerabilities. Always harden your servers, review your configurations, and never deploy with defaults. In our next video, we'll explore another OWASP Top 10 vulnerability, so stay tuned. If you found this useful, hit like, subscribe to Secure 7, and share this video with your friends. Welcome back to Secure 7. In today's video, we're exploring another critical OWASP Top 10 vulnerability, sensitive data exposure. Every day, organizations handle personal data like passwords, financial information, and health records. But what happens when this data is not properly protected? It becomes a goldmine for attackers. In this session, we'll break down what sensitive data exposure is, real-world examples, how attackers exploit it, and how you can prevent it. And as always, this video is for educational and ethical hacking purposes only. What is sensitive data exposure? Sensitive data exposure occurs when an application unintentionally reveals sensitive information to unauthorized parties. This usually happens because of poor or missing encryption, weak security practices, or misconfigurations. Imagine you're logging into a website that doesn't use HTTPS. Your username and password travel over the network in plain text. If someone intercepts that traffic using a tool like Wireshark, they can see your credentials instantly. That's sensitive data exposure, and it's surprisingly common. Why it's dangerous. Why should you care? Because exposed sensitive data leads to account takeovers, identity theft, credit card fraud, large-scale data breaches that damage brand trust and cost millions. In fact, many breaches you've heard of in the news started with this simple issue. Real-world examples. Let's look at some examples. In 2013, Yahoo suffered a breach that exposed over 3 billion user accounts. Weak hashing and poor security practices contributed to this. In 2017, Equifax leaked personal information of 147 million people due to an unpatched web server and unencrypted sensitive data. These cases prove that even big companies are vulnerable when proper data protection isn't enforced. Demo concept: how exposure happens. Now let's walk through a simplified demo concept. Picture a login page using plain HTTP. A user enters credentials. An attacker on the same network runs a packet sniffer like Wireshark. Because there's no encryption, the attacker sees the username and password in clear text. Alternatively, imagine a database storing credit card numbers without encryption. If an attacker gains read access through an injection vulnerability, they get all the data in plain text. This is why encryption at rest and in transit is critical. Types of sensitive data. What qualifies as sensitive data? Here are some examples. Personally identifiable information, PII, names, SSN, addresses. Financial data, credit card numbers, banking info, authentication data, passwords, session tokens, API keys. Health records, medical history, prescriptions. If attackers get this data, they can commit fraud or sell it on the dark web. How attackers exploit it. Sensitive data exposure can happen in many ways. Applications using outdated or weak encryption like MD5 or SHA-1, not forcing HTTPS, allowing man-in-the-middle attacks, leaving cloud storage buckets publicly accessible. Improper access control, where anyone can download backups or logs. Attackers actively scan for such weaknesses. Automated tools make it easy to find unprotected data sources. How to prevent sensitive data exposure. Now let's talk prevention. Protecting data requires several layers of defense. 1. Use HTTPS everywhere. Install a valid TLS certificate and enforce secure connections. 2. Encrypt sensitive data at rest and in transit. Use strong, up-to-date algorithms like AES 256 for storage and TLS 1.3 for transmission. 3. Avoid storing unnecessary data. If you don't need it, don't keep it. 4. Secure encryption keys. Store keys in a secure vault, not in your source code. 5. Regularly rotate and update keys and certificates. 6. Implement proper access control. Ensure only authorized people can access sensitive data. 7. Scan and monitor for exposure. Use tools to detect misconfigurations and leaks early. Following these best practices drastically reduces your risk. To summarize, sensitive data exposure happens when organizations fail to protect critical data properly. Attackers exploit this to steal identities, commit fraud, or sell data. The good news? With proper encryption, secure configurations, and data hygiene, you can prevent most of these risks. If you found this video helpful, don't forget to like and subscribe to Secure 7 for more ethical hacking tutorials and OWASP Top 10 breakdowns. And remember, knowledge is power, but only when used ethically. Welcome back to Secure 7, and today we're diving deep into one of the most dangerous but often overlooked OWASP Top 10 vulnerabilities: software and data integrity failures. This vulnerability doesn't rely on brute force, password guessing, or even misconfiguration. Instead, it exploits the trust you have in the software you use and the data you rely on. We'll explore real-world examples like the SolarWinds hack, walk through a demo showing how this works, and most importantly, learn how to prevent it. Grab a coffee, sit tight, and let's get started. What is software and data integrity failure? So what does this term mean? At its core, software and data integrity failure occurs when applications or systems fail to verify the integrity of software updates, libraries, or critical data. If your system downloads a file or update and assumes it's safe, without checking its authenticity, attackers can exploit this trust. Think of it like receiving a sealed letter. If you never verify whether the seal is genuine, anyone could slip malicious content inside. Some common cases include applications using unsigned or unverified software updates, dependency confusion, pulling packages from untrusted sources without integrity checks, continuous integration pipelines with weak access controls, apps loading external resources like JavaScript libraries directly from a third-party CDN without verifying a checksum or signature. This is how attackers launch devastating supply chain attacks. Let's look at some real-world incidents. SolarWinds supply chain attack 2020. Hackers compromised the SolarWinds Orion update system. Organizations like Microsoft and several U.S. government agencies installed the Trojanized updates, allowing attackers to infiltrate their networks. Event Stream NPM package incident 2018. An attacker added malicious code to a popular JavaScript library, stealing cryptocurrency wallet keys. Kodakov Bash Uploader 2021. A malicious update sent sensitive data from CI/CD environments to an attacker-controlled server. What's common here? The attacker didn't exploit the victim directly. They compromised a trusted source. Here are the main reasons this vulnerability occurs. Close quote bot 1. Unsigned or improperly validated updates. Many applications don't check digital signatures on software updates. 2. Untrusted dependencies. Developers often pull packages from open-source repositories. If an attacker uploads a malicious package with the same name as an internal one, dependency confusion, it may get installed. 3. Weak CI/CD security. If an attacker can modify build pipelines, they can inject malware directly into production code. 4. No sub-resource integrity, SRI. Websites loading scripts from external sources without integrity checks allow attackers to inject malicious JavaScript. Impact of exploitation. Attackers can execute remote code on victim machines, steal sensitive data, credentials, and encryption keys, deploy ransomware across thousands of systems simultaneously, compromise a single vendor, and impact thousands of customers downstream. This is why the SolarWinds hack was so catastrophic. Open quote, what's the worst that can happen? Close quote. How to prevent it? Luckily, there are strong defenses against this vulnerability. 1. Code signing. Always verify the authenticity of software updates using digital signatures. 2. Sub-resource integrity, SRI. Add integrity attributes to externally loaded scripts. 3. Pin dependencies. Lock versions and use package checksums. 4. CI/CD hardening. Implement MFA and restrict access to your build pipelines. 5. Regular security audits. Monitor open-source dependencies for known vulnerabilities. To wrap up, software and data integrity failures are deadly because they exploit trust. Always verify updates, check dependencies, and secure your CI/CD pipelines. If you learned something today, like and share this video, and subscribe to Secure 7 for more in-depth OWASP Top 10 tutorials with real demos. Next up, we'll cover security logging and monitoring failures. Stay tuned. Welcome to Secure 7. Today's deep dive is into SQL injection, one of the most common and powerful vulnerabilities in web applications. We'll explore how it works, demo real attacks, use tools like SQL Map, and show you how to defend against it. Grab your notes. This one's packed. Let's start with the basics. SQL stands for Structured Query Language. It's how websites talk to their databases. Whenever you log in, search, or submit data, the backend often uses SQL to retrieve info from a database. Here's a typical SQL query. Select char from users, where username equals admin and password equals 1234. SQL injection happens when a hacker enters malicious input that changes the query's logic. If someone types this into a login form, or 1 equals 1, the new query becomes select show from users where username equals, or 1 equals 1, and password equals. And guess what? That always returns true. The attacker logs in without valid credentials. This works on search fields, URLs, contact forms, anywhere user input gets passed into SQL without validation. Let's demonstrate this on DVWA, Damn Vulnerable Web App. I've set the security level to low for testing. Here's a form that asks for a user ID. If I type 1, it returns user details. Now watch what happens when I inject. Or 1 equals 1. Boom. It returns all user records. We just bypassed authentication. This shows how easy it is to exploit poorly coded applications. Now let's use a real-world tool, SQL Map. It automates SQLi attacks in seconds. Run this command, sqlmap-u http:/localhost/vuln.php1 id 1-dbs. This command tells SQL Map to test the target URL and extract database names. As you can see, it detects the injection point and pulls out all databases. You can go further with flags like Nash tables, dump, or even OS shell to gain remote access. SQLi isn't just about login forms. There are different types, and each is more stealthy than the last. Classic, visible error-based, like we just saw, inject something and the server responds with data or error messages. Blind SQLi, the server doesn't display errors. So attackers ask true or false questions to extract data slowly. Example, and 1 equals 1 and 1 equals 2. Time-based blind attackers use sleep functions to test the server's behavior. Example, or if 1 equals 1, sleep 5, 0. If the server delays, the condition is true. If not, it's false. Bit by bit, the attacker reconstructs data. Out-of-band SQLi data is exfiltrated using DNS or HTTP requests. This only works if the server allows external calls. Ethical hackers use various tools to detect and exploit SQLi. Tools include SQL Map, automation and database dumping, Burp Suite, intercepting and manipulating requests, OWASP Zap, active scanning for SQLi, Postman or curl for custom payload testing, WFuzz or FFUF for fuzzing input fields. These tools are easy to learn and used in bug bounty, pen testing, and even red teaming. So how do we stop SQL injection? Use parameterized queries, prepared statements. Never insert raw user input into SQL. Use prepared statements instead. Example, cursor.execute, select char from users where username equals and password equals, UP. Input validation and escaping. Validate data types. Escape dangerous characters like quotes, semicolons, and comments. Least privilege access. Your database users should only access what's necessary, not everything. Web application firewalls, WAF. Use WAFs to block common attack patterns like or 1 equals 1, regular code audits and penetration testing. Test before attackers do. Use automated tools and manual testing. SQL injection has caused real damage in the past. Examples: 2012 LinkedIn, 6.5 in user passwords stolen, Sony Pictures, massive breach via SQLi, US voter database, exposed via a simple SQLi script. Even major companies get breached when they ignore the basics. Let's recap. SQL injection is simple, powerful, and still one of the most exploited vulnerabilities today. But with the right coding practices, parameterized queries, validation, and testing, it's completely preventable. Thanks for watching Secure 7. If you found value in this video, hit that like button, subscribe for weekly cybersecurity content, and share this with your fellow hackers. Want to learn more? Check out our full ethical hacking course, linked below. Next up, we cover broken access control, another critical web vulnerability.